So in this video we are going to start talking about chemical reactions. And now we're basically getting really into the heart and soul of chemistry, because chemistry is by definition the science that's concerned with how matter is organized and how one type of matter is converted into another, and how the conversion of one type of matter into another, how does that occur? It occurs through chemical reactions. So we're going to start out by talking about properties of water, because we're going to first talk about reactions that take place in aqueous solution. In other words, take place in water. So water is a covalent molecule, but specifically it's a polar covalent molecule. Well, what does that really mean? We said that covalent bonding is based upon electron sharing, whereas ionic bonding is electron transfer. But that doesn't necessarily mean if a molecule is covalent, that doesn't necessarily mean that the electrons will be shared evenly. Okay, so for example, if we have a water molecule, okay, the electrons most definitely are not shared evenly. They spend more time with the oxygen than they do with the hydrogen, and so you wind up with a partial negative charge on the oxygen atoms and partial positive charges on the hydrogens. Not full-blown charges like you see in ionic compounds, but partial charges. All right? So when dissolved in water, ionic compounds dissociate into their parent ions, okay? And these ions become solvated by the water molecules, right? So there's forces of attraction between oppositely charged ions, even the partial charges that you see in water. So if you have an ionic compound, it dissociates into the positive and negative ions, and so the positive ions are attracted to the partial negative charges, in other words, to the oxygen atoms, and the negative ions are attracted to the partial positive charges, in other words, to the hydrogen ions. Okay, and I drew this out. So, for example, assuming that you have salt, let's say sodium chloride, right? So you have the full-blown positive charge on the sodium and the partial negative charges on the water molecules, and there's a force of attraction here. And then the same thing over here, except it's the chloride ion is negative, so it's going to be the positive parts of the water molecules are going to be attracted to the chloride. Okay. So what are some examples of dissociations? That this is sort of good practice to think about this sort of thing. So, for example, sodium chloride, that's easy. It's a 1-to-1, +1, -1. So it's going to dissociate into one sodium ion and one chloride ion. Okay. Now, magnesium chloride. Magnesium is a 2+ ion. So you have to have 2 chloride ions in the formula to balance the charge. So when that goes into solution, it's going to give you 1 magnesium ion and 2 chloride ions. Okay? And so, for example, sodium sulfide. Now, sulfide is a -2, so you have to have sulfide is a -2 ion, so you have to have 2 sodium ions up front to balance the charge, right? So that's going to give us 2 sodium ions and 1 sulfide. But what about polyatomic ions? You should sort of treat these indestructible units. Okay, so even later when we get into balancing these balancing equations, predicting formulas, treat them as indestructible units. So for example, when the sodium nitrate dissolves up in water, it gives you 1 sodium ion and 1 nitrate ion. Don't try to break up the nitrate into nitrogen and oxygen. So treat the dissolving of sodium nitrate as no different than, let's say, that of sodium chloride. Okay, same thing with the magnesium nitrate. Treat that just like the magnesium chloride. So we're going to get one magnesium and two nitrates, two nitrate ions. And then my last example here, ammonium carbonate. That's where both the cation and the anion, both the cation and the anion, are polyatomic ions. So that's going to dissolve up to give us two ammonium ions and one carbonate ion. Okay? Now that's only true of ionic compounds. Covalent compounds do not break up. Okay, so when covalent compounds are dissolved in water, there's no breakup. So for example, sucrose, C12H22O11. Oh, it dissolves, yeah, but it doesn't break up when it dissolves. You just simply have C12H22O11 molecules in solution. Okay, now there's a few covalent molecules, and we'll talk more about this later, that undergo partial dissociation. So for example, acetic acid. You're going to see later this is what we call a weak acid. But notice I've replaced the arrow, the one-way arrow, with an equal sign. It really should be a double arrow. Okay, but this dissociation does not go 100%. It only goes part the way. In fact, it only goes to a very small extent. Most of your acetic acid is over here in the undissociated form. Okay, so ionic compounds break up into their ions. Covalent compounds do not. And then you have a few that undergo partial dissociation. Okay, so electrolytes are solutions that dissolve in water to produce solutions that conduct electricity. In other words, the resulting solutions are electrically conductive. Okay, so you have strong electrolytes, weak electrolytes, and non-electrolytes. Okay, so a strong electrolyte is a substance that dissociates completely into its ions. Okay, so the solutions are good conductors of electricity. But pretty much any soluble ionic compound, because that ionic compound is going to fall apart into its ions. Okay, the weak electrolytes are where the dissociation occurs only to a small extent, like the acetic acid. Okay, and then non-electrolytes are compounds that do not dissociate at all. Basically, most covalent compounds. Okay, so there's a classic. I'm not going to actually do the demonstration, but there's a classic demonstration that you can do, basically showing solutions that conduct electricity. Right? So we could have a beaker here, let's say, with a couple of electrodes in it. Okay, so this is what we call a series circuit. A series circuit. Basically, then, that for the electricity, for this light bulb to light, your electricity is going to have to make a complete circuit. Okay, so say we have this hooked up to, say, a battery, let's say positive and negative power supply. What's going to happen? Electricity is going to have to flow through the wire to the electrode and into the solution. There's no connection between these two electrodes except for the solution. So electricity is a flow of electrons that have to go through the wire, through the electrode, and then into the solution, pass through the solution to the second electrode, and then basically through your light bulb, and then back to the power supply. So for the light bulb to light, this solution has to be able to conduct electricity. Electricity has to, it's part of the circuit. When we say these two are in series with one another, but electricity has to flow through the solution. Now, if you put pure water in there, the light bulb won't light. unless your pure water is tap water that's really, really, really bad. Most likely that's not going to be the case. Pure water, and certainly for pure water, it won't light. Okay. If you put a non-electrolyte like sugar, like a covalent compound, it won't light. And if you put an ionic compound in there, if you dump salt in there, it'll light. Okay. If you put something like acetic acid, let's say the weak acid, and we said that's a weak electrolyte, okay, it would light, yeah, but it would light a little bit, okay. So, if it's a strong electrolyte, the light bulb will light. Non-electrolyte, it will not light, and a weak electrolyte, it will light a little bit, okay. So let's talk about metathesis reactions, also called double replacement reactions, also sometimes called precipitation reactions. Okay, so we're going to start out by talking about this reaction between silver nitrate and potassium chromate. Okay, if you mix the solutions together, you'll see it precipitate, sort of a brick red silver chromate precipitate. Okay, so the reaction is 2 silver nitrates, and this is already balanced. So silver nitrate plus potassium chromate gives you silver chromate plus potassium nitrate. Okay. AQ, these symbols in parentheses basically refer to the state of the reactants involved. AQ means aqueous, in other words, dissolved up in solution, and S means solid or a precipitate. A precipitate is a solid product that falls out of solution. You might also see L for liquid or G for gas. So both of these are ionic compounds, silver nitrate, potassium chromate. So in solution, the silver nitrate exists as separated silver ions and nitrate. Okay? And in solution, the potassium chromate exists as separated potassium ions and chromate ions. Okay? So when you first mix it, you could either pour one solution into another, or you could pour them into a third container, but temporarily at least, all 4 ions can come in, or you have all 4 ions present in the same solution. Okay, so initially we had silver and nitrate and potassium and chromate, and then we can mix them. When we mix them together, then the potassium can potentially come into contact with the nitrate, and the silver can potentially come into contact with the chromate. And silver chromate is not soluble. If you had some solid silver chromate and you try to dissolve it up, you stand there and stir it all day, it's not going to dissolve. So when you mix the two together, the silver starts pairing off with the chromate. Those ions fall out of solution, and that gives you left behind a solution of potassium nitrate. So silver chromate is insoluble. Okay, and so the silver ions and the chromate ions pair off and begin pairing off and basically falling out of solution because they're producing insoluble silver chromate. Okay, so where we're going with this, we're going in a couple of different places with this, but one of which is for you to be able to predict whether a pair of ions or solutions will produce a precipitate. You have 2 solutions, you mix them together, will you get a precipitate? Okay, so to be able to answer a question like this, you have to understand the solubility rules. So what types of compounds are generally soluble, what types are not. So let's talk about soluble compounds first. Okay, so generally all common compounds of group 1A's and ammonium are soluble. Okay, and by group 1A we're talking about that first column on the periodic table, the alkali metals, they're all soluble. I can only think of maybe one exception, maybe two, to that rule that all your 1A compounds are soluble, and ammonium compounds. Okay, so all nitrates, acetates, and most perchlorates are soluble. Okay, if you don't know your polyatomic ions at this point, this might be a good time to go back and review them. Right, nitrate is NO3 minus, acetate, CH3, COO minus, perchlorate, ClO4 minus. Okay, all common halides, chlorides, bromides, iodides, are generally soluble except for silver, lead, copper, and mercury 1, mercury Hg2, 2+, which is really mercury 1. And then last, all common sulfates, or tend to be soluble. Remember, we're talking about generally soluble compounds, except for calcium, strontium, barium, and lead. Okay? So, what are some compounds that are generally insoluble? So these are compounds that are generally insoluble with some exceptions. Okay? So, metal hydroxides tend to be insoluble. The only exceptions are those of group 1A and the larger members of group 2A, beginning with calcium. Okay? All common carbonates and phosphates are insoluble, except for, again, 1As and ammonium. Okay? And then all common sulfides. Sulfide is just S2 minus. Okay? Are insoluble except when paired again with group 1As, 2As, or ammonium. Okay? So, let's classify each one. Let's classify each one of these compounds as soluble or insoluble. Alright, so aluminum carbonate. So carbonate is one of your compounds. Carbonate is one of your compounds that are typically insoluble, with the exception of the 1As and ammonium, right? Aluminum is not a 1A, and it's certainly not ammonium, right? So that's insoluble. Okay. Lead iodide. Now we said the halide ions, chloride, bromide, and iodide are generally soluble with exceptions, but lead was one of the exceptions, so that is insoluble. In fact, lead iodide produces a very, very bright yellow, golden, orange, yellow colored precipitate. Okay. Potassium sulfate, generally insoluble except with 1As. Potassium is a 1A metal, right? It's an alkali metal. That's going to be soluble. Magnesium hydroxide. Hydroxides typically tend to be insoluble with some exceptions. And magnesium is not one of the exceptions, so that's insoluble. Okay. Now, sodium perchlorate. One of our rules was that all perchlorates tend to be soluble, so that compound is soluble. Right, and then ammonium chloride. Well, chlorides typically tend to be soluble, and one of our rules was that all ammonium compounds are soluble, so that one is definitely soluble. Alright, so let's predict. So now let's predict. Let's carry this one step further now. And let's predict whether each pair of solutions will produce a precipitate when it's mixed. All right. So we'll swap the ions around. So if we mix sodium hydroxide and potassium nitrate, what are our products? What are our products going to be? Potassium hydroxide plus, so right, we're swapping the ions around. Okay, so the potassium will move to be paired with the hydroxide and the sodium with the nitrate. So the question is, are these soluble? Well, one of our rules was all nitrates are soluble, right? So that's soluble, and all our hydroxides are insoluble except with alkali metals. Potassium's an alkali metal, so that's soluble, So basically no precipitate. So really, in a sense, you can mix the two reactions together, but nothing is really going to happen. Okay, nothing's really going to happen. Okay, what about if we mix silver nitrate and sodium chloride? Okay, again, we're going to swap the ions around. So what are we going to produce? Silver chloride plus sodium nitrate. So that's the same product as up here. All nitrates are soluble. What about the silver chloride? Chlorides are typically soluble with some exceptions. Silver is one of the exceptions. So basically, here we'd get a precipitate. We'd get a precipitate of silver chloride. Okay. So we're going to mix together potassium iodide and lead nitrate. So what our product's going to be? Lead iodide and potassium nitrate. Okay, so are either of those going to be soluble? Well, all nitrates are soluble, so that one is not going to be a problem. But lead iodide is an example from the previous slide. I said that one is insoluble. So we would have a precipitate there. And then our last example, if we mix together sodium carbonate and calcium nitrate, we swap the ions around. What are our products going to be? Calcium carbonate and sodium nitrate. You ought to know by now that's soluble. What about this, calcium carbonate? Go back and look at your rules. Carbonates are generally insoluble with some exceptions. Calcium's not an exception. So that one is soluble. Okay, so in these last three ones, we would get a precipitate. Now, let's go in. And I want to practice. I didn't balance those previous equations, and I want to go in and practice balancing some of these equations. So, first, let's look at this first example. We're going to mix aluminum nitrate and sodium carbonate, and that's going to give us a precipitate of aluminum carbonate. That's not soluble. That's our precipitate, plus sodium nitrate. So the way I would do this, the way I would balance this, I would start with the aluminum carbonate, the precipitate, right? Al2CO3. So we know we're going to have to have two aluminums on the right side of the equation. All right. So on the left side we have aluminum nitrate. There's only one aluminum and aluminum nitrate. So we're going to have to put a 2 in front of the aluminum. Now granted, that 2 is going to operate on this whole formula. So if aluminum nitrate consists of 1 aluminum and 3 nitrates, we now have 6 nitrates on this side. Okay, we'll worry about that in a minute. So we balance the aluminum. Now what about the carbonate? We have 3 carbonates. Al2CO33, right? So we're going to put a 3 in front of the sodium carbonate. Okay, and that 3 operates in front of the whole formula. So basically we now have 6 sodiums. So we have 2 times 3 is 6, so we have 6 Na plus here. Okay, and 3 times 2 is 6, so we have 6 nitrates here. Right, so we're going to put a 6 in front of the sodium nitrate, and that's balanced. Okay. Second reaction, ammonium sulfate reacts with lead nitrate, and that's going to give us lead sulfate plus ammonium nitrate. Now, the lead sulfate's not soluble. That's our precipitate. Obviously, ammonium nitrate is soluble. Okay, so this ought to be easy. Let's see, lead sulfate. There's only 1 lead ion and 1 sulfate in lead sulfate. Now we have a bit of a problem with the ammoniums. There's 2 ammoniums here, and only 1 ammonium and ammonium nitrate, so we're going to have to put a 2 there. Okay, and that gives us 2 ammoniums and 2 nitrates. And we already have 2 nitrates here. So that's pretty much here all we have to do to balance the equation. We don't really have to write the 1s. If you don't see a number, then the 1 is implied. I'll go ahead and write them in. Okay. Okay, let's look at our last example here. Reaction between calcium chloride and sodium phosphate to make calcium phosphate, which is insoluble, plus sodium chloride. Okay, so again, let's work off our precipitate. Our precipitate was calcium phosphate. Okay, so Ca3PO4 Alright, so we're going to have, so basically we have 3 calciums in this formula. So we're going to have 3 calciums on the right side. We're going to have 3 calcium ions on the left side. There's only 1 calcium and calcium chloride, right? So we're going to have to put a 3 there. Okay. And what about our phosphates? Phosphate is, we have 2 phosphates here, right? Because when that 3 calciums and 2 phosphates, there's only 1 phosphate in sodium phosphate. So what are we going to put there? We're going to put a 2 in front of the sodium phosphate. And now we only have the NaCl to balance. How many chlorides do we have here? 2 times 3 is 6. We have 6 chlorides there. And 2 times 3 is 6. We have 6 sodium ions there. Okay, so we're going to make 6 salts, or 6 sodium chlorides. And that equation is balanced. That's very much like the first one that we did. Alright, so there's one last thing I want to talk about here with regards to metathesis reaction. And there's 3 ways to write an equation for aqueous reactions. Okay, so the first of all is what we call the molecular equation. Okay, so the reactants and products are written as if they are undissociated and intact compounds. So back to the reaction, or back to a reaction, a similar reaction to the one we started with talking about. Silver nitrate and sodium chromate gives us silver chromate and sodium nitrate, right? So silver chromate's a precipitate and sodium nitrate is soluble, so it's aqueous, so that means it remains in solution, okay? This is the molecular equation. We write everything as if they're undissociated and intact compounds. In other words, we know silver nitrate is soluble. That AQ means that we know it's soluble. That means in solution. And we know that it's really separated into Ag plus and NO3 minus, but we're going to write it this way in the molecular equation. Okay? So this is inaccurate, because we know that anything that's soluble is dissociated into ions. The silver nitrate, the sodium chromate, the sodium nitrate, everything but the solid is dissociated into ions. But that's the way we write it in a molecular equation. Okay? And then in the ionic equation, we write all soluble ionic compounds as ions. In other words, so instead of AgNO3, we write 2Ag plus and 2NO3 minus. Okay, we recognize now we're recognizing that this is really dissociated into Ag plus and NO3 minus. Okay, and the sodium chromate we write as 2Na plus and CrO4 minus. Now, the silver chromate, we leave it written like this. Why? Because that's the solid. That's not dissolved. That's what falls out of solution. That's a solid. Okay, so that really isn't dissociated. That really exists as Ag2CrO4 solid. All right, and then the sodium nitrate exists as Na plus and NO3 minus ions, right? So that's the ionic equation. Also sometimes called the total ionic equation. Okay. Now, last we write what's called the net ionic equation. Okay, and this eliminates the spectator ions. Okay, so what are spectator ions? So why do we call them spectator ions? Because they don't really participate in the reaction. So basically anything that appears as an ion on both sides of the equation we cancel out. Okay, so we can cancel out, we have 2 nitrates on the left and 2 nitrates on the right, and 2 sodium ions on the left, and 2 sodium ions on the right. Those are all spectator ions. We can cancel these out, and what are we left with? The 2 silver ions and the chromate combine to form the sodium chromate. So basically, all the ions cancel out except for those that are involved in the formation of the precipitate. And that gives you the net ionic equation. So molecular equation, everything is written in molecular form. Ionic equation, everything is written as separated ions except for the solid. And then the net ionic equation, we cancel out all the ions that appear on both sides of the equation. And that wraps up this discussion. Next, we'll talk about acid-base chemistry, acid-base reactions.